This video is going to look at a couple more examples of the first derivative test. And the first one we have here is f of x equals x plus 1 over x. And again, our first step is to find the derivative. So first of all, you may want to rewrite this function as f of x equals x plus x to the negative 1. And then if we calculate the derivative of this function, we have 1 minus x to the negative 2, which is really 1 minus 1 over x squared. And once we have our derivative, we know that if we're trying to find our critical numbers, we're going to set the function equal to 0 and solve for x. So here if we if we multiply here, we can move the 1 over rather, and we would have negative 1 over x squared equals negative 1. And if we multiply both sides by x squared, we have negative 1 equals a negative x squared. And then from here, if we switch sides, we have x squared equals 1, and therefore x is equal to plus or minus 1, because if we take the square root, remember that would be plus or minus the square root of 1. So here we have our two critical numbers, and before we go any further, are these going to only be the two critical numbers for this example? Do we have any other critical numbers? Well, keep in mind our critical numbers occur when our derivative equals 0, or when what? Or when our derivative is undefined. And if you notice here, we have our derivative is 1 minus 1 over x squared. Well, we know that our denominator here cannot be equal to 0, so what's going to happen here at x squared if x is equal to 0? So that tells us that x equals 0 would also be a critical number, because what that tells us is our function is not differentiable at 0. So here we have three critical numbers, plus or minus 1 and 0. So our critical numbers, we have negative 1, 0, and 1. And you'll notice when I write down my critical numbers, it's best to put these in order from smallest to largest, negative 1, 0, 1, because now when we go to create our test intervals, we know that we need to test from negative infinity to negative 1, and then we need to test between negative 1 and 0, and then between 0 and 1, and then of course we have to test from 1 to infinity. So because we have three critical numbers, we're going to have 4 test intervals. And then if we pick our test points, once again, you want to pick the easiest number in between negative infinity and negative 1. I would pick negative 2. Negative 1 to 0, I would probably pick a negative 1/2. And 0 to 1, I'd pick a positive 1/2. And 1 to infinity, 2. So then we need to evaluate the sign of our derivative at negative 2. And if we plug a negative 2 into the derivative, and to save us time here, you're simply taking these values again and plugging them into the derivative. And if we plug those into 1 minus 1 over x squared, clearly when you square the negative here, we're going to end up with 1 minus a fraction here. So we are going to end up with a positive. And if we have a positive, that tells us our function is going to be increasing. And if we evaluate at negative 1/2, what's going to happen? Well, if you plug a negative 1/2 in, you're going to end up squaring and multiplying by the reciprocal, and you're going to notice you end up with a negative. So therefore our graph is decreasing. And if we continue on, if we plug in 1/2 into the derivative, you're going to find out that's going to also be negative. So that means our graph is going to continue to decrease from 0 to 1. And then if we evaluate our derivative at positive 2, what happens? Well, if you plug 2 into the derivative, you're going to end up with 1 minus 1/4. So of course that's going to be positive. So once again, from 1 to infinity, our graph would be increasing. So that tells us on the interval -infinity to -1, and then from 1 to infinity, our graph is increasing. And -1 to 0 and 0 to 1, which we could simply say from -1 to 1, our graph is decreasing. So that tells us if we are going to increase to this point and then decrease, that's at our -1. So that tells us at -1, we're going to have a relative max, and that's going to be at -1. And if you plug -1 into the original function, you would find the y value is equal to -2. And then our graph decreases and decreases, but then over here at 1, it's going to decrease and increase at this point. So therefore, we would have a relative minimum. And that's going to occur at 1. And if you plug 1 into the original function, your corresponding y value is 2. Now be careful, when we're looking at these points for relative max and relative min, recall we're taking the x value here, -1, the x value +1. We're going to plug those into the original function because we want to find the y coordinate. We're looking for the actual point on the graph of the original function. So -1, -2 is the relative max, 1, 2 is the relative min. And once again, we could look at the graph over here on the right. If we graph the original function, we can see that we're going to have a relative max at -1, 2, which is this point here. And then you're going to have a relative minimum, which we said was at 1, 2, which is this point here. And we can certainly see that the graph is going to change directions. In other words, our slope here is positive, and then over here it decreases, and then it's decreasing and increasing over here. And you notice the graph at 0, what's happening? There's a split in the graph. Well, if there's a split in the graph here at 0, that means that it is not differentiable. And you can tell over here we saw that from our first derivative here. Because of the 0 here, our graph is not differentiable at x equals 0 because there's an actual break in the graph. So you can determine that from the function that it's undefined or not differentiable because of the break in the graph. Or if you look at the derivative itself, what's going to make the derivative undefined? You know, in other words, typically you're looking at what's going to cause you division by 0, or if you happen to have a negative in the square root or something of that nature. So here, even though we had a critical number at 0 because of this split in the graph, in this case, the undefined part, not differentiable, is not a relative max or relative min. Okay, our next example here, if you notice here, we have some trig functions. F of x equals the square root of 3 times sine x plus cosine x. And notice here, we're only going to look at this on the interval from 0 to 2 pi. Okay, and the reason we're going to do that, for example, if we look at the graph down here below, we can see that we know when we deal with our trig functions, a lot of cases we're going to end up with a graph that is oscillating. So it's going to kind of continue forever here, oscillating up and down. And that's why we're going to go from 0 to 2 pi. So if we look at this graph from 0 to 2 pi, this is what we're looking at here. So we're looking at basically here kind of one period of this graph. Now we can probably look over here and we can kind of guess and say, well, we're going to end up with a relative max at this point and a relative minimum at this point. So we can always look at this graphically and locate our relative min and relative max. But let's see if we can apply our first derivative test to identify those points. Well, if we take the derivative, once again here, the square root of 3 is just going to be a constant multiplier, so we can bring that down. And the derivative of sine is cosine. And then the derivative of cosine is a negative sine. Okay, so there's the derivative. And we want to know where's our slope going to be 0, so we set the derivative equal to 0. And at this point, we can divide everything by the cosine of x. So basically, we're going to divide both sides of the equation by cosine. And by doing that, if you notice here, we're going to end up with the square root of 3 minus now sine over cosine. That becomes the tangent. And 0 divided by anything over here, we know that's going to be 0. Now, why did we divide everything by cosine? Because by doing so, we actually eliminated one of our trig functions, so that now the equation only has one trig function, which is the tangent. So then we would end up with negative tangent x equals negative square root of 3. Simply move the square root of 3 over. And now to make these positive, of course, we can multiply or divide by a negative. So the tangent is equal to positive square root of 3. So we need to identify, you could actually use the calculator or you could use your unit circle. Where is our tangent equal to the square root of 3? Now remember, tangent is y over x. So at what angle on our circle, if we think of our unit circle, on the unit circle, where do we have the square root of 3? In other words, where is our y coordinate divided by the x coordinate equal to the square root of 3? And you're going to notice that's going to occur at pi over 3 and 4 pi over 3. So at these places, if you take your y divided by x, that's going to give you the square root of 3. So we have two answers. Now, if you prefer here at this point, if you wanted to, you could look at this as a decimal. The pi over 3 is approximately 1.04, and 4 pi over 3 is approximately 4.19. So there's your critical numbers, pi over 3 and 4 pi over 3. And is the derivative undefined anywhere? Well, if we really look at the interval, now keep in mind, we're only looking at the interval from 0 to 2 pi. We could actually look at the graph, and we can tell from the graph it's a nice, smooth, continuous curve. There's no gaps, there's no breaks, no sharp turns. So it's going to be differentiable on the entire interval 0 to 2 pi. So our only critical numbers are pi over 3 and 4 pi over 3. So the test interval. Now notice our test interval here, we're going to end up with 3 intervals. But notice here, I'm not going to say negative infinity, because remember our interval up here was 0 to 2 pi. So we're going to look from 0 to pi over 3. And then we're going to go from pi over 3 to 4 pi over 3. And then from 4 pi over 3, and notice here I'm not going to go to infinity, we're going to stop at 2 pi. And again, that's because of the interval up here from 0 to 2 pi. So now we need to pick a test point within inside of each of these intervals. And pi over 3, again, if it helps, pi over 3 is 1.04, so we could easily plug in a 1. And pi over 3 to 4 pi over 3, if you want to change those to decimals, you have 1.04 to 4.19. So I would simply pick 2. And then something greater than 4 pi over 3, Since 4 pi over 3 is 4.19, we could simply pick 5. And once again, if we evaluate the derivative at 1, and that simply means we plug 1 into the derivative up here, we're going to end up with, I'll just go ahead and tell you, that's going to be a positive number. And then if we take the next test point 2, plug that into the derivative, we're going to end up with a negative. And if we evaluate the derivative at 5, we get a positive number. So positive tells us here our graph is increasing, a negative tells us the graph is decreasing, and then again we have a positive, so the graph is once again increasing. So if we're going from increase, decrease to increase, that means we're going to have a relative max, and then we would have a relative min. And that's exactly where we had indicated before. We have a relative max here at pi over 3 and a relative min here at 4 pi over 3. And that's kind of what we concluded, because we can see here clearly our graph changes directions here from increase to decrease, so we would have the relative max, and then from decreasing to increasing we would have a relative minimum.